Welcome back to our organic chemistry playlist. Today we're going to be talking about alcohols, and this is going to be this entire series here is on alcohols. Here I have a cute little picture of ethanol dog, and just so you're aware, this series is going to run congruent with the organic chemistry textbook from David Klein's, the 4th edition of that book. So the things we're going to cover in this series is we're going to start with the properties of alcohols. We're going to go to the preparation of alcohols, kind of a review of Organic Chemistry 1. We're going to see ketone reduction. Alrighty, we'll get into that then. Diol preparation, how can we make diols to alcohol groups? We're going to look at Grignard reagents. We'll see those. Does similar things to ketone reduction. We're going to look at the protection of alcohols and alcohol reactions. How do alcohols react with other molecules? And then we're going to look at the oxidation of alcohols and phenols. All right, so getting into the introductory concepts here. What is an alcohol? Right? It's the thing you drink, right? That's ethanol. But what overall, when we are talking about organic chemistry, is an alcohol? It's any molecule with an OH group on it. They tend to be at least somewhat soluble in water because of that OH group. You can see in the figure here, I have a molecule of ethanol with that OH, and we can see hydrogen bonding with water, right? And only a few alcohol species are actually fully miscible in water. The difference between soluble and miscible is that miscible means you could put any amount in there and it's going to dissolve that much, right? So if I had 100 grams of water and I put in 100 grams of ethanol, it's going to dissolve all 100 grams of ethanol. If I put in 120 grams of ethanol, it's going to dissolve that. Granted it could. Alrighty. So I actually have a list over here of a trend that we'll see with the solubility at just 20 degrees Celsius of alcohols. We have methanol, ethanol, 1 propanol, 1 butanol, 1 pentanol, 1 hexanol. So that's just like alkanes, right? And then at the end we add an OH group. We can see that the smaller we are, if we're a methanol, we're just a CH3 group and then an OH, we're going to be fully miscible. Same until we get up to the propanol one, right? That becomes miscible as well. And then for every liter of water, for butanol, we can dissolve 1.06 moles per liter of that. And then we see the solubility rapidly decreases. And that's because if we were to look at these molecules, we know that the hydrocarbons are nonpolar. And those will exhibit their own intermolecular forces called London dispersion forces. They cannot do hydrogen bonding, and because of that, the solubility drops, right? There's more of that interactions between themselves than there are with water. And for that reason, again, solubility decreases. Okay, so now we're going to look at the acidity of alcohols. Alcohols, we know, are acidic from losing the hydrogen on their oxygen. Right, so if we look at the figure down here, we go from an alcohol, right, that R just means the rest of the molecule, usually just an alkyl group will say, like, propanol. Well, this is propanol. We have a base here, it comes in, and it's going to deprotonate that alcohol, and we're going to get something called an alkoxide. That's the conjugate base of an alcohol. All right, so some important notes, you need to use a base higher than the pK of the alcohol you're trying to deprotonate. That's just so you'll get a favorable equilibrium, right? And hopefully, for the most part, negligible of the product you don't want. So we know that the pK of alcohols are about 15 to 18, so you have to use a pretty strong base, right? Good bases, for example, can be NaH. This is a wonderful base, it's called sodium hydride. When it couples with a hydrogen, it's going to bubble out as hydrogen gas. So if you have a container there, it's going to be an irreversible change. If I have 10 moles of alcohol and I put the equivalent amount of NaH in there, it's going to irreversibly turn all 10 moles of that into alkoxide ions. Okay, another base that we can use is NaNH2. Remember that our nitrogen bases are pretty good, right? The pK of that is like, I believe, in the 20s, even the 30s even. I forget It's been a while. But we know it's a very strong base, but there will be some equilibrium there. So it's not as irreversible as NaH, but still a good base and will get the job done quite well. Alrighty, and then finally we can use alkali metals like lithium, sodium, or potassium. These metals are going to make an ionic bond with the alcohol, the alkoxide, right? And that's going to form that ionic salt, right? And then we just get our hydrogen ions swimming around doing what they love. So, alrighty, so adding on to what we said about the acidity of alcohols, we know that not all alcohols are made equal, right? Some are stronger, some are weaker than others. This is due to things like resonance. We'll see that with phenols in just a second. Induction with trichloroethanol, for example. And then we have solvation effects with tert-butanol. So let's look at those individually. Okay, so we have our first molecule here, phenol, right? And we're going to explain why resonance can make some of these alcohols stronger, and a good example is phenol here, right? So ethanol's pKa is about 16. When we look at phenol, this pKa is about 10. All right, so that is about 1,000,000 times stronger, or 100,000 times stronger than each other. So the phenol here is 100 times stronger as an acid, but why is that? Well, let's see here. So if we were to just do with sodium hydride, do an irreversible deprotonation of this phenol, right? So we use the amount we need. We'll get something like this. And then we're going to get oxygen with a negative charge. Alrighty, so there's some resonance here. Right, so we said resonance is important. Well, let's see the resonance structures. We have a full negative charge here, and we know that's quite unstable. So we can neutralize it by doing the following. Resonance structures, and then we'll put the negative charge here, right? And we have some ketone character there, and we have a negative charge here, and then this will go around the ring till we get back to where we were. So we'll put a negative charge here, so let me draw that quick. And then finally, we're going to put that there and then move that negative charge up here. So we'll get something like this here. Oh my goodness, what am I doing? Negative charge. Very nice. Alrighty, so when we look at all the resonance forms here, we can see that when we deprotonated it, it looks like we have a full negative charge right here. And that would be unstable, right? So the reverse reaction would be kind of favorable because we could go in the reverse direction. We know that this is this right here, since we used an irreversible base, that this is irreversible. But if we use, say, like sodium NH2, well, this reaction would have some sort of equilibrium. But the pKa of this is about 10 because this negative charge here is stabilized. It gets some ketone character, neutral character, we should say. So we have 1, 2, 3 molecules where we have a neutral charge on the oxygen, and only one has a negative charge, right? So because of that, the pKa of resonance stabilized alcohols are going to be a lot lower, meaning more acidic, than other alcohols like ethanol, for example. Alrighty, so now I want to look at the effects of induction. Remember, induction is just, okay, molecules are pulling electron density away, like chlorine, for example, bonded to a carbon. The electronegativity difference favors the electron density going towards a chlorine. So I'll just draw that here. So if we have a carbon, and I'll just draw chlorine in a different color. If we have a carbon-chlorine bond, remember there's electrons going all through here, right? All in that bond. That's what attracts them, right? But we know that because chlorine is more electronegative than carbon, we have that electron density wanting to go more towards this way, right? More towards the chlorine. So when you were to, if you were to look at, okay, the average spot of all electrons, you'd probably find it like kind of like this, right? Right, where more of the electrons are towards the carbon or the chlorine than the carbon. And that's exactly what's happening here, right? Remember that we make a negative charge, right? So I have this reaction here with NH2 of this trichloroethanol, oh my goodness, forming that alk oxide conjugate base, right? This is a negative charge, but it's kind of stabilized through these chlorines. Why is that so? Let me just come over here a little bit. So if we have, I'm going to draw out every single bond here, except for the hydrogens, because those suck. Who likes those? Okay, so just to prove my point here, chlorine has a dipole this way, same with this one, and same with this one. So this carbon here feels a little partially positive. Alright, and that causes this carbon to feel a little partially positive, because it feels that induction, right? So there's a dipole here, which then causes this oxygen atom to have a slight dipole. And that's going to lower the energy of this negative charge, right? So that means that it's a less reactive species, because if we lower charge, it becomes less reactive. And therefore, we would assume the pKa of this reaction to be lower and more acidic because it's more stable, the resulting product that you get. We know that induction isn't really as strong as resonance, but it still has an effect. When we look at ethanol's pKa, it's about 16. When we look at the pKa of trichloroethanol, it's going to be about 13. So that means about 100 times more reactive, 100 times more acidic, I should say, than ethanol. And that's just because of induction. Okie dokie, so for our last little part here, we're going to look at what's called solvation effects. Maybe you looked at this, maybe you didn't. I'm just going to write it out here, solvation effects. And this has to do with steric hindrance. It's back again once more. We saw it in aromatic reactions. Now it's back in our alcohol reactions. So if you feared it, you better fear it again because it's back. So solvation effects basically says to what extent can water neutralize that negative charge. So here we have the conjugate base of two alcohols. We have ethanol's conjugate base and tert-butanol's conjugate base here. So we know that the tert-butanol's conjugate base, right, is a lot more sterically hindered, right? If I was water and I wanted to come into this molecule, where could I attack from? Well, I can't really come in through here because I'm blocked by that carbon, so that's a no-go. Can't come from this carbon side because that's a no-go. I could sure come in from the front, right? So I'm going to draw a water molecule. Remember, the hydrogens are the partially positive part of the molecule, so it's going to interact here. And we could come in through here, right? And we could even like come in through here. And so there's all those partial positive charges neutralizing that negative charge. What happens when we look at ethanol, for example? Where can it attack from? Well, let's start with where it can't. Well, it can't come from like that side, right? Because it's blocked by a carbon. Yeah, it can't. The only way it can't come down is through that carbon right there. But it can come in through here. It can come in through the front, of course. It can come in through here, the top even. And I think you're starting to see the point here that I'm trying to make. It can come in through here. And you're also going to see an explanation for the solubility we talked about just a little bit ago. It could even come in through here if it wanted to. Now this is very dramatized, but I wanted to make the point here. When we look at which alcohol's conjugate base feels more, which alkoxide feels more negative, you're probably going to say it's this one, right? Because there's, let's just take this for example, 1, 2, 3, 4, 5, 6. There's 6 molecules here that are stabilizing that negative charge. 6 partial positives from that water molecules. But here there's only 3, and we're going to draw 3 with a sad face. 3 with a sad face, right? So we would expect that this is more negative, and because of that, if you were to react this with a base, there's going to be some equilibrium going this way. So the pKa of this one is actually higher. We'd expect a pKa of about 18. That's a total guess, but I assume. And this one will have a pKa of about 16, right? Or the pKa of this molecule, and then the pKa of this one being this molecule when we're talking about pKa's. So that was solvation effects. Hopefully that makes sense. That was the first episode of our alcohol reactions. Hopefully you guys enjoyed. I plan to make a couple more videos, as you saw in the little content sheet in the beginning. Make sure to stay tuned, and I hope you guys have a wonderful day.